Hi there, and in this video we're going to look at monotonic sequences. Okay. So we're here on page 3 in the notes in section 1.2. So a monotonic sequence is one that is either increasing or decreasing. Okay. So the definition here in definition 1.3 is fairly straightforward. We say that a sequence of elements xn is increasing if its elements satisfy this chain of inequalities. So each element of the sequence is less than or equal to the following element. And we say it's decreasing if the inequalities go the other way. Okay, if each element of the sequence is greater than or equal to the following element. So x1 is greater than or equal to x2, x2 is greater than or equal to x3, and so on and so on. We also have the terms strictly increasing and strictly decreasing. So we would say xn is strictly increasing. Well, that's just if all these inequalities are in fact strict less than or greater than. So xn is strictly increasing if and only if x1 is strictly less than x2, and that in turn is strictly less than x3, and that in turn is strictly less than s4, and so on and so on. So this would be, say, an infinite sequence beginning at the index n equals 1. And strictly decreasing would be the corresponding definition. Now, if you're given a formula for a sequence or a recurrence relation for a sequence, one quick way of investigating it is to plot the first few terms of the sequence. So let's take an example sequence here, n squared plus 2 divided by 2 to the n. Okay, the sequence of elements fn. Now the commands in MATLAB that you would need to do to get a plot of this are shown here. We'll have a look at those in a moment, and there's also shown some Sage commands below. Let's go to our MATLAB window. So I'm in a MATLAB live script here. So this first line defines what is known as an anonymous function f. So it's just a quick one-line command for defining a function that you're going to use in other commands. So this function, the syntax here is you say, so f is going to be the function name, the variable we're going to store the function in. And we say f equals, so at the at symbol at n, so that indicates that n is the argument to the function, and then whatever follows that then is the value of the function evaluated at n. So it's n squared plus 2 divided by 2 to the n. This example we're going to look at. Capital N we set to be the array of integers from 1 to 100, and then this function array function applies the function f to the array n, and gives us an array s of values of this function. Okay, so I'm going to take that off there so we can see the output here, and then the command plot s will simply plot the elements of the array s, and it will use a dot for each point. Okay, so you can see the output of the array s here. If you click into that, you can. Okay, so these are all the values of n squared plus 2 divided by 2 to the n. Of course, when you're dividing by 2 to the power n, as n increases, this is going to get small very, very fast indeed. And you can see that in the plot here. Maybe the first couple of elements you might have equality there, the first couple of elements, but after that you can see the elements are all decreasing. And you could even hazard a description there and say that this sequence is converging to 0. More on convergence later. So that's how you can take a particular formula for a sequence and quickly get MATLAB to quickly show us a plot of the first few terms of the sequence. We'd expect that, we'd expect to be able to describe the sequence as a decreasing sequence. Okay, but it must be said that we're only looking at the first few terms here. This is an infinite sequence. We might need a slightly stronger argument to show that this sequence is increasing all the time, or is decreasing all the time. Let's just look at Python to see how we do this similar thing inside Sage. So here I'm in a Sage worksheet on the Calc service. So you can program in Python here, much like you did using Jupyter notebooks in your programming skills unit. The difference here is we're not dealing with raw Python here, so we're dealing with Sage's implementation of Python here. So there's a lot of mathematical functions which are preloaded that we don't have to import and that are available to us here using specific Sage commands. But raw Python will work in here as well. So this function we're looking at is n squared plus 2 divided by 2 to the n. So if I want to start investigating this, I could, well, it's various ways. One kind of naive way of doing it would be to start off with an empty list S, and then start a loop, a for loop. So you could say for n in the range 101. Well, let's say started at 1. So this range command, range from 1 to 101, this will give me an iterator of the integers starting at 1 and ending at 100. It ends at 1 less than the ending argument. So this will give me this for loop here, and then I could append onto a list. So if you have a list in Python, you can append, which means add an element to the end of the list. So we'll append what, n squared plus 2, n squared plus 2 divided by 2 to the n. In Sage, because Sage is oriented towards mathematics, Sage understands this caret notation for denoting powers. Remember, if you're in Python, you would represent, raw Python, you would represent exponentiation with a double asterisk, but Sage understands the typical maths notation of this caret symbol to denote powers. So if we execute that, then that simply defines our list S. So you can look at S. You'll see here that Sage is working exactly, so it represents each of these quantities using exact fractions. Okay, but I mean, you can't tell you can't tell much from just looking at those big fractions. But there's a command in Sage, list plot. So list plot S. Oh, I think I need an underscore there. List underscore plot S then produces a simple scatter plot of those sequence elements, much like we just saw in MATLAB. We could draw the same conclusions from looking at that. Now, there's a neat way in Python for doing this kind of thing quickly, rather than creating an empty list first and then using a for loop to one by one step through all the values of the index and each time adding an element onto the end of the list. You can do it all in one line using a so-called Python list comprehension. So list comprehension and similar set comprehensions and other data type comprehensions is a way of defining something where you might have naively defined it using a for loop there, to just do it all in one line. And the advantage of it is that it's quite reminiscent of our mathematical set notation. So let me type out a list comprehension here that will generate exactly the same list S that we just generated. So we're going to say that S is going to consist of the quantities n squared plus 2 divided by 2 to the n for every n in the range 1 to 101. Okay, so for a mathematician to type that is quite natural, because it looks like our set builder notation. S is, okay, it's not a set here, it's a list. S is a list of the quantities n squared plus 2 divided by 2 to the n for every n in this range of values. Okay, so that defines our list S, which you can then graph with the same list plot command to investigate the sequence. Okay, so that's how to use Sage and MATLAB to investigate some of these sequences where you have a nice formula for it. But what if we just wanted to get a little bit more rigorous and actually prove the monotonic behavior here? Okay, so there's some remarks here just kind of stressing that they need to be able to come up with a stronger argument to prove this. Well, there's two ways to do it. We might do it. We can either look at the difference between neighboring elements in the sequence and compare that to 0. Because if you can show that an plus, if you're talking about a sequence an, if you can show that an plus 1 minus an is always bigger than or equal to 0, that will show that the sequence is increasing, okay, because you'll have shown that an plus 1 is always bigger than or equal to an. And also, if you show that it's strictly bigger than 0, then you'll have shown that it's strictly increasing. And similarly for decreasing sequences. So that's, you can prove the increasing or decreasing nature by comparing to 0. You can also look, instead of looking at the difference between neighboring terms, you can look at the ratio between neighboring terms, and instead compare that to 1. Okay, so if you show that, if you examine the ratio an plus 1 for just a general value of n and compare this to 1, well, if you show that is strictly bigger than 1, then that's equivalent to an plus 1 being strictly bigger than an. Okay, so in other words, this is i.e. a strictly increasing sequence. Strictly increasing sequence, that would be. We're going to assume here, assuming that these ans are all positive, strictly positive. Okay, we have to avoid 0 if we're going to talk about an in the denominator, and to draw this conclusion here about multiplying both sides by an, we need to know that an is a positive number. So otherwise it would reverse the direction of the inequality. So this gives us two ways to investigate the monotonic behavior. You can either examine the difference between neighboring elements and compare it to 0, or you can examine the ratio between neighboring elements of the sequence. If you know that they're all positive, examine the common ratio and compare that to 1. And if it's bigger than or less than 1, you'll be able to draw the conclusion about the sequence increasing or decreasing. So here's an example here that we can work through, example 1.6. So we're going to investigate the sequence an. Let's say this begins at 1, goes to infinity, where an is given by this formula, 5 to the power n over n factorial. Now, you've got a choice here. Do you look at the difference between neighboring terms and compare to 0, or look at the ratio of neighboring terms and compare to 1? Well, for things like exponentials and factorials, they cancel very easily when they're put in ratio. Similar exponentials and similar factorials will cancel quite a lot when you divide one by the other. Okay, so notice here that an is strictly positive for all n bigger than or equal to 1. So we'll examine the common ratio. So we'll look at an plus 1 divided by an. So just fill in each term of the sequence here. So an plus 1, this will be 5 to the power n plus 1 divided by factorial of n plus 1. And we're looking at the ratio of that to an itself, which is 5 to the power n divided by n factorial. Okay, well, let's kind of straighten these fractions out so we can examine what's happening. So we got 5 to the power n plus 1, and this n factorial will come up to the numerator, and then you've got 5 to the power n by the factorial of n plus 1. Now this is going to simplify an awful lot, isn't it? For instance, all these 5s are going to cancel and just leave 1 5 in the numerator position. In addition, all the factorials cancel and just leaves a factor of n plus 1 in the denominator. Remember, the definition of a factorial is n factorial is n times n minus 1 times n minus 2. It's the product of all the positive integers down to 1, say. So n plus 1 factorial is almost the same. It's just you've got an extra factor of n plus 1 at the beginning. So, you know, all the factors in n factorial cancel out with their the same factor in n plus 1 factorial, leaving just the quantity n plus 1. And comparing to 1 now, we see that 5 to the power n plus 1, this is going to be greater than 1 for the first few values of n. Greater than 1 for n equals 1, 2, and 3. It's equal to 1 for n equals 4. But beyond that, once n reaches 5 or beyond, and this number is going to be strictly less than 1. Okay, for n greater than or equal to 5. So for n greater than or equal to 5, we have that an plus 1 divided by an is strictly less than 1. Okay, so i.e. an plus 1 is strictly less than an. So it's a decreasing sequence. It's a decreasing sequence for n greater than or equal to 5. So that example shows us one way that we can prove the monotonic behavior of a certain sequence. We could check and verify that using Python, using Sage. So we could define, let's give it a different name. Let's call it T, or let's call it A. A being the list of this sequence. So we want to look at 5 to the power n divided by factorial of n plus 1. Okay, so that's how you write it out in Sage. And we want to look at these elements for n in the range, let's just go 1 to 20. Here's our sequence of elements A, fair enough, and let's just plot them. Yeah, so you can see this behavior here. The first few terms of the sequence are increasing, then it kind of plateaus. You got two elements the same, but after that it becomes a decreasing sequence. So the sequence is monotonic from 0.5 and 0.5 and beyond. Okay. But still, looking at the plot only shows you what's happening for a certain, initial set of elements. In order to rigorously prove it for the whole sequence, we need a kind of general argument like we just saw on the board. Okay, we could have a look at another example. So this example isn't in the notes, so another example. Consider the sequence Sn defined by this formula. So Sn is going to be 3n over 4n plus 1. Is this sequence monotonic, and is it increasing or is it a decreasing sequence? So let's consider the difference. We'll consider the difference Sn plus 1 minus Sn, and we'll compare it to 0. Okay. So Sn plus 1 minus Sn. Well, Sn plus 1 is going to be 3 times n plus 1 divided by 4 times n plus 1 plus 1. And then minus Sn is minus 3n over 4n plus 1. Now we're subtracting fractions here, and we want to compare it to 0. So the best way to compare it to 0 is to put this as a single fraction over a common denominator. The common denominator we could use would be simply the product of these two things. So you got 4 times n plus 1 times 4n plus 1. And then in the numerator, on the one hand, we'd have 3 times n plus 1 times 4n plus 1. And then we'd have minus 3n into 4 n plus 1 plus 1. Now, let's just think about this before we launch into a load of algebra. Ultimately, I'm going to be comparing this to 0. I want to know if this is bigger than or less than 0. Now, you notice that the denominator part, whatever it is, it's certainly positive for all n bigger than 1, bigger than or equal to 1. So the status of the whole fraction, whether it's bigger than or less than 0, is going to be determined by the status of the numerator. So I can ignore the precise form of the denominator here because I can see here that it's always going to be positive. So I can just focus on the numerator here. So I'll just put, just put this set of brackets here just to indicate this denominator there. I'm not going to look at that any further. So let's see what we have in the numerator. Well, let's simplify the second one first. So you got minus 3n into, so this is 4n plus 5. Isn't it? So when you multiply this out, what are we going to get here? We're going to get 3 into, we're going to get 3 into 4n squared. Then you got 4n plus 5n plus 1. And here you have minus 12n squared minus 15n. But you see here, when you expand out this first bracket, you again get 12n squared plus 15n. So this 12n squared plus 15n is going to cancel with these minus 12n squared and minus 15n. So in total, you're just going to be left with 3 in the numerator. And you've got that denominator, whatever it is up there. So it's clear how this compares to 0. This number is strictly bigger than 0, okay? For all n bigger than or equal to 1. Okay, and we can make that conclusion because the denominator, as we've said, is always a positive number. Okay. Right, so what have we done there? Okay, this fraction is bigger than 0, but what is this fraction? This fraction is the difference between Sn plus 1 and Sn. So we've shown here that Sn plus 1 minus Sn is strictly bigger than 0, i.e. we've shown that Sn plus 1 is strictly bigger than Sn. And we've done this for all n bigger than or equal to 1. So that means this sequence is an increasing sequence. Okay, that's our conclusion. So Sn from n equals 1 to infinity is an increasing sequence. We say a strictly increasing sequence, in fact. A strictly increasing sequence. So it's a monotonic sequence and it's strictly increasing. Okay. So you'll find some more examples to look at in the tutorial sheets. Yeah, we got one little definition here we could consider. This is where we're starting to look at the kind of this monotonic property. You can say is a property of the whole sequence. Yeah, the whole sequence. If the sequence is monotonic, it means it's always increasing, or it's always decreasing. So it's a property of the whole sequence. Another property you can say is whether or not the sequence is bounded. Okay, so a bounded sequence is a sequence where there's going to be some upper limit m to the absolute value of the elements of the sequence. Okay, so a sequence is bounded if there exists some positive number m, such that for all values of the index n, the absolute value of the sequence element is less than or equal to m. You can pick that apart and look at the two concepts of being bounded above and bounded below. So this is where we drop the absolute value signs. And the sequence xn is bounded above if there exists a number capital M such that xn is always less than or equal to m. And it's bounded below if xn is always bigger than or equal to bigger than or equal to capital M for some choice of number capital M. Okay, so in the next video we'll go on to look at the concept of convergence, and then the tutorial sheet you'll find some more examples of sequences where you can practice proving the monotonic nature of the sequences. Okay, so I'll see you in the next video.